All right, welcome back to the new session. So, in this session, you're going to understand how, as a programmer, you write some program, and then all these things are being converted, and computer does something with it. All right. The secret is that it is electrons that actually do the whole job. You're going to see how electrons, okay, do this job. That's what we are going to show you in this session. So, how do we get electrons to do the work in a computer system? Because it's actually electrons that actually do the job. So how do we do this? So let's take you through this journey and show you how this thing works. So what are electrons and why do they matter? Okay. First of all, you remember in secondary school, we were taught electrons in chemistry and also in physics. So electrons are negatively charged subatomic particles that orbit the nucleus of atoms. I'm not too much interested in the definition, okay? But you know what electrons are, and the movement of electrons in a wire is what we call electric current, okay? So they are fundamental to electricity and thus to electronics, including computers. Remember that computers are electronic devices. They are electronic devices. They cannot work without electric current, okay? So when electrons move through a conductor, all right, it is called an electric current, all right? So whenever, I believe some of you know these things already, okay? When electrons are moving through a conductor, something like a wire, a copper wire, okay, there is an electric current. So the movement of electrons is what we call electric current. Then computers harness this current. Computers take advantage of this electric current in a controlled way. There is a way computer controls this electric current, and in this way, they can use this controlled way electric current to store data. They can use it to process data, and they can use it to transmit information. You see everything that happens around your computer, whether transmitting information from one network to another, all these things that is happening, transmitting data from, you can be streaming a video live. These things are just done by computers controlling controlling this electric current. Basically, that is what it is. So let's make you understand how these things work. So now the question is, all right, the question is, how do we control this movement of electrons? Because we said that computers harness this current in a controlled way. So computers have to control this electric current to maybe use it to store data, process, or transmit information. So how do we control the movement of electrons to achieve meaningful work? Now, this takes us to what we call the source, okay? Now, the source, okay, there should be electricity, all right? Electricity powers electron movement. Without electricity, these electrons, there will be no movement of electrons. That is why your system has to be on, like it has to be plugged, or the battery has to be on. So this computer requires electric power, either from a battery or from an external source, okay? Your mobile phone uses battery, your laptop uses battery, you can plug them and recharge them, stuff like that. But the thing is that your computer needs a source of electricity. So it is through this source, it is the electricity that powers the electron movement. There has to be electric current flowing through these wires. And basically, your computers are just made up of wires, transistors, that's what we call it. But we are going to show you, or as we go, you're going to understand these things, okay? Now, this electric power, they create a voltage difference. It's a kind of pressure. Okay, so this voltage difference that pushes electrons, it is the voltage difference that pushes electrons to materials like copper and semiconductors. All right, but in this case, we call them transistors. Okay, it is the transistors that actually do all these things. Okay, so these transistors are where these electrons and the voltage differences actually occur. I'm not going to go deep into it, but as we go on, we'll be unfolding it bit by bit. Okay. So when there's electricity source, this electric power creates a voltage difference that pushes electrons. So the electron movement that you want, okay, is being provided through the electricity, okay? But just pushing electrons isn't enough, all right? Yes, when you have electric power, all right, when you have source of electricity, it creates the electron movement, and this movement actually creates a voltage difference, okay? Now, but this voltage difference or this movement of electrons, they are not enough. We need to control them precisely. We need to control this flow of electrons. Okay, when to flow, where to flow, and how fast they can flow. Now, when we talk about controlling when to flow, remember your switch. Okay, you have switches on the walls of your house. Okay, when you switch it on, there is electricity will flow. When you switch it off, there will be no electricity. So that is basically how we use transistors to do the same thing here. Okay, so that is where transistors and logic circuits now come in. Now look at it. First of all, we need electrons need to flow to create electric current. Do you understand it? So with the flow of these electrons, the electric current that is being created, computers can harness this electron movement. Now, but the thing is this, computers take advantage of this electron movement. They use it to store data, process data, or do whatever they do with it. But how do we get these electrons to move? We get these electrons to move through electricity. It's either the electricity is coming from a battery or it's coming from an external source. Okay, now, when this electric power will create a voltage difference that causes these electrons to move. But the thing is that the movement of electrons or pushing of electrons, they are not enough. We need to control these electrons. And how do we control these electrons? We use transistors. All right, so this is where we get to transistors. Transistors are the smallest unit of a computer system. Then, when we put transistors together, we will get logic circuits. Do you understand? So that is how we get here. So now let's talk about transistors, okay? Because transistors are like switches, all right? Just like the switch on your wall, you switch it on, there is the electric current, you switch it off, there's electric current. So transistors can switch on or off. So when the transistor switches on, the computer will see it as 1. When it switches off, the computer will see it as 0. We are coming to that, okay? So a transistor is the most fundamental component in modern electronics. All right? Transistor is like the cell in the body. It is the most fundamental component. It acts as a switch or amplifier and is made from semiconductor materials like silicon. All right, silicon is what we use to create transistors. Now remember, semiconductor material, that means transistors can conduct electricity. Do you understand? When these electrons flow through conductors, all right, there will be electric current. So transistors conduct electricity, and that is why there is electric current through transistors. So it's like a switch, or it acts as a switch or amplifier. Now, there are billions of transistors. In the previous session, we mentioned that modern computers have billions of transistors. CPUs, GPUs, etc. There are billions of transistors, okay? Now, each transistor controls the flow of electrons. Now, my question is, how do we get electrons? Remember, we get electrons through electricity. Do you understand? The electricity power that we get from either our battery or plugging our system to an external source. But the electricity will cause the electrons to flow, but now we need to control this electric current so that we can actually make use of it, store data, process data, or transmit data. Then we now use transistors to control the flow of electrons. I hope you're getting it, okay? Now, transistors can be turned on or off. When the transistor is turned on, it is 1. When it is turned off, it is 0. That is why you see data is stored in computer in zeros and ones. Computers only understand zeros and ones. So now, how do we get, when we want to get a 1, we bring a transistor that has current, that is on. When we want to get a 0, we bring a transistor that is off. We are coming to that. You're going to understand that better as we go on, okay? So you're going to see that most of the things we call something like circuit, logic gates, and co, they are just made of different transistors. So if a transistor is on, you can have to, if you want to represent a number, something like 0, the binary value of 0 is 0, 0. So if you want to represent a number, that means you bring two transistors that are off, because they have to be 0, 0. So if you want to represent 1, 0, 1 is the binary value of 1. That means you bring one transistor that is off and one transistor that is on. But don't worry, as we go, you're going to understand better, okay? So when you turn a transistor on, the computer sees it as 1, and when it is turned off, the computer sees it as 0. So this transistor, they act like a binary switch. And this is the basis of all computing that I just mentioned now. These transistors, they act like binary switch. They are either on or off. So when a transistor is on, it is 0. When a transistor is off, it is carrying 1. Okay? So they act like binary switches, and this is the basis of all computing. Now, these on and off states form the foundation of the binary number system. Remember that computers use binary number system. They don't use the decimal or octal or hexadecimal. No, they use the binary system. So it is through these zeros and ones. Remember, binary system is 0 and 1. So on and off of these transistors will give us either 0 or 1. Do you understand it? Don't worry, as we go on, you're going to understand better. So now let's talk about the binary system, okay? Ones and zeros represent everything in the computer. Now, how do we get to 1 and zeros? We got to 1 and zeros by the on and off states of transistors, remember. And how do we get transistors? We get transistors into the system because we need transistors to control the flow of electrons. We control the flow of electrons. And how do we get electrons to flow in a system? We have to get electric power. All right. And then why do we need electrons? Because the flow of electrons causes electric current. I just took you back to where we came from. Okay. So now binary system, ones and zeros. Electrons don't know about words or pictures. They only flow or stop. Electrons are either flowing or they are not flowing. So when they are flowing, they give us 1. All right. When they are not flowing, they give us 0. So that is the zeros and ones. Okay, so that is what computers are actually using to, this is the basis of computing. All right, zeros and ones. Electrons don't know whether you have an image or whether you have a video. All your videos, all your data, they are stored in zeros and ones. So electrons is either flowing or they are not flowing. This simple concept is represented as 1 means that current is flowing on a transistor. That means the transistor is on. 0 means that there is no current. All right. So it's either there is electric current or there is no electric current. Remember, okay? So using patterns of these ones and zeros is what we call bits. Do you understand it? Bits are the simplest the simplest data type, the simplest way to represent data. Zeros and ones. Okay. So numbers like if you want to represent 65. In binary format, this is how you represent it. It is 0, 1, 0, 0, 0, 0, 0, 0, 1. So that means we are going to use how many transistors to represent this 65? 1, 2, 3, 4, 5, 6, 7, 8. We are going to use 8 transistors, all right? So if you want to represent 65, this 65 is using 8 bits. Each 0, 1, 0, 1, they are all bits, all right? So the 0 is a bit, 1 is a bit. So we are going to use 8 bits to represent this binary representation of this 65, okay? So we will use, the first transistor is going to be off, the second transistor is going to be on, the next one will be off, the next one will be off, the next one will be off, just like that. This is how these things work, okay? So when you represent letters, now when you type a letter, all right, when you type a letter, there's something we call ASCII code, Unicode. We'll talk about that later on. But when you type a letter on your keyboard, the computer has a mechanism of converting it to a number, all right? And you convert it to there are predefined numbers created for these things. So A is equal to 65. Then once the computer converts your letter A to 65, if you want to store it in the computer or make use of it, it will now convert it to binary number, which is now this one that we are seeing on the screen, okay? So still on binary system, your images are also represented in zeros and ones. You can represent images in bitmaps. Now, these are different data types, or you can represent it in pixel, all right? So the data type for representing images, we call them either bitmaps or pixel. You're going to understand better, but the bottom line is that your images are represented in zeros and ones. Even your sound, your video, they're all represented in zeros and ones. Your programs, even the program that you write, they are represented in zeros and ones. You're going to see more of that. As a programmer, you're writing a program, they're all represented in zeros and ones because your computer only understands zeros and ones. If you're bringing anything that is not 0 and 1, your computer will not understand it. So, but you're going to understand when you write a program, how do we convert it to what the computer would understand? In this session, we are going to talk about it too, okay? So everything in your computer, video games, your websites, your documents, is ultimately a pattern of binary bits controlled by electron flow. Do you understand it? So basically, it is your transistor that is used to control all these things. Okay, so your transistor is the most fundamental component of your computer system. So everything, any data you have, they are stored in patterns of binary bits, zeros and ones. All right. So now, from these transistors, all right, we now get logic gates. Do you understand it? Transistors are what we use to control the flow of electrons. But now, when we put these transistors together, all right, transistor for me, let me give it's like a wire. Let me put it like that, a wire that conducts electricity. So if you want to form a logic gate, all right, you put up transistors together, one or two transistors together. We are going to teach you more about logic gates later on and transistors. But for now, when you put transistors together, they will form logic gates. So to do useful work with ones and zeros, we organize our transistors into logic gates. It is the logic gates that do the computation in your system. When you say 1 plus 1, down the system, it is the logic gates that perform that arithmetic. Your CPU is built with logic gates. Okay, so transistor put together will give us logic gates, and we have logic gates like the AND gate. The AND gate, it will output 1 only if both inputs are 1. So the AND gate will take 2 transistors. All right, will take 2 transistors as inputs. If both transistors are current are flowing, that means they are 1. Both of them are 1. The AND gate will produce 1. If any of them is 0, the AND gate will produce 0. But don't worry, we're going to go deeper into logic gates. But just understand that transistors put together, 1 or 2 transistors put together, 2 or more transistors put together will give us logic gates. And it is logic gates that perform the computation. We are going to see all these things. So we also have the OR gate. The OR gate will output 1 if if at least one of the transistors is 1, that means it is on. We also have the NOT gate. The NOT gate will invert the input of a particular transistor. Okay, don't worry, you're going to understand these things better as we progress. All right, so we also have the XOR, the NAND, and the NOR. We are going to discuss logic gates later on. But transistors are what we put together to get logic gates. Then logic gates put together to get logic circuits. All right. So by combining logic gates, we will get logic circuits. When you combine logic gates together, 1 or 2 logic gates, that is where you now build arithmetic units. Those units that perform additions, multiplications, we call them adders or multipliers. Okay. So we create memory. So it is from this logic gates that you create your memory. Then you're going to see how beautiful this thing is. From transistors controlling the electrons, we put them together to form logic gates. Then we will now put logic gates together to form our arithmetic and logic unit. All right. So we will also use these logic gates to create memory devices. So basically, logic gates, after transistor, logic gates is what we use to build the computer. So we form the basis of the central processing unit using logic gates. Do you understand? Okay. So transistors will put together to give us logic gates. We'll put logic gates together to create all the different components of your computer. The central processing unit, the control unit, everything, every component of your computer are being created. It is a composition of 1, 2 or more logic gates. So logic gates are the thought process of the computer, how it makes decisions based on the instructions you give it. So logic gate is the thought process. Where computation occurs in your computer is on your logic gate. Everybody is using AI now, or we are using robots. Your robots, every decision they make or any computation they do, it goes down to the logic gate. So it's the logic gate that actually perform all this. So the thought process of your computer is your logic gate. Okay. Now, we now put these logic gates together to create the CPU. The CPU is the brain where electrons do the thinking. Logic gates are the thought process, but it is the CPU, which is the brain of the computer, that is where the electrons now do the computation. Okay, so central processing unit is the heart of the computer where most calculations happen. But remember, CPU is made up of 1 or 2 logic gates, okay? Now, inside the CPU, control units, inside the CPU, we have the control unit. The control unit fetches and decodes instructions. Don't worry, we are getting to that, okay? Now, as a programmer, when you write your instructions, okay, these instructions are stored in memory. So your CPU will not fetch, this control unit will not fetch this instruction stored as zeros and ones in memory. When they fetch them, they will not decode them. So they will not be the one to say, okay, this particular code is for addition or this particular code is for subtraction. So it is the control unit that fetches and decodes these instructions. You can see that computer science is very, very interesting. Very, very, very interesting. And when you understand these things, you can write better programs, okay? Now, the arithmetic logic unit does anything that has to do with math and logical operations, okay? It is the arithmetic unit. But remember that it is the logic gates that we put together to form all these components that we are now talking about. So we also have registers. Registers are small memory. Now, because the control unit, when they want to fetch data or instruction, they go to the hard drive. So, and it is actually slow. So as computers were evolving, they now created small memory units that are very close to the CPU. Don't worry, you're going to see all these things play. So we have registers, or we also have cache, okay? So these are used for faster data fetching, okay? So all these components are built from transistors. You understand? From transistors and logic gates. 1 or 2 transistors make up a logic gate, and 1 or 2 logic gates make up all these components we are talking about, all the components of your computer. And they control the electron flow to carry out millions to billions of instructions per second. How do we even get to a CPU? Remember, we started with electrons, all right? We started with electrons, the movement of electrons, creating electric current. So this electric current, how do we get them to move? We have to plug them to an electric source. And with this electric source, there will be electric movement, electric current. And then how do we control this electric current? We started using transistors, on and off. On is 1, off is 0. And how do we, these transistors put together will give us logic gates. Logic gates put together will now give us other components of the system. All right, it's so interesting. Now, memories, your memory is also a component of your system. So this is where electrons are held. Okay, your memory holds electron states over time. So your memory is holding zeros and ones. Do you understand? So your memory is where we store data. So those data that we are storing we are storing those electrons from those transistors. So at a time, if you still want to use it to bring it up again. So your memory is just storing data in zeros and ones. And remember, these are electrons from transistors. So memory stores data in the form of electric charges, either 0 or 1. All right. So memory components are also made up of transistors and logic gates. So random access memory stores data temporarily. You know this one already. When the power goes off, data is lost. Okay. But don't worry, we also have a section on memory. All right. On the memory component, we have a section. So we also have flash drive and also SSD. They store data using floating gate transistors that trap electrons even without power. Okay. Then we have hard drives that store data magnetically, but ultimately use electric signals to store, read, and write. Now, RAM is temporary storage, flash drive or flash storage, your SSDs, your hard drives. These are permanent data storage. All of this, again, comes down to controlling electrons. All right? All this data that we are storing in memory and everything we are talking about, they all comes down to electrons in a precise, reversible way to remember ones and zeros. Do you understand? Okay. Then when we talk about how data flow through the system, you're going to see that data flow is actually electric current. It's either that a transistor is carrying an electric current or it's not carrying an electric current. That is how we do zeros and ones. Okay. Now, input and output. So you input, you'll be the one to give the computer data. So when you input, when you type something on your keyboard or when you use camera to get input, we talked about input devices and output devices before. Okay. So now when you give input, whether you use camera or you use scanner, whatever input device you use, the computer will convert all these things to electrons. Okay, input devices, keyboard, mouse, microphone, they are converted to physical signals. All right, and they are also they convert input devices. Now, the input devices, our keyboard and our mouse, they convert physical signals to electrical signals. So your keyboard, when you type something on your keyboard will convert it to electrons. All right. So output devices, when the system, the computer processes data and they want to give it to you for you to see, the output devices, the computer will give it to the output devices, and the output devices will convert them to electrons too. Okay, so they convert binary data into visible, audible, or physical forms using controlled electron movement. That is what we have just explained. Everything in computer is about controlling the movement of electrons. And how do you control the movement of electrons? We control movement of electrons using transistors. And transistors are now the basis of all the components we have, our logic gates, our central processing unit, our memory, and everything. Okay, so example is this. In a screen, binary values control voltage to each pixel, deciding which color to show. Don't worry, we'll talk about images, video, and data representation in general, okay? Now, in a speaker, binary sound data becomes voltage waves that move a diaphragm, creating sound waves, all right? But basically, your input and output devices, they convert, they move electrons in and out. They move electrons in and out, okay? All right. So now it comes down to software. Okay, now this is where we come in. We programmer, this is where we come in. We write the software. Okay, so these softwares are instructions we write. Now, if you want to solve a problem, you will have to write it in software for the computer to solve the problem for you. Now, this software that we write, most times we are writing this software in something that looks like English or any other language you speak. So how does this computer know what to do with all these electrons? All right. That's the rule of software. So in your software, as a programmer, you're writing instructions. Now, the computers don't know how to make use of these electrons. They say that the computer is an idiot. It's an electronic idiot. The computer knows how to control and move electrons, but they don't know how to use these electrons to solve problems for us. When you say, computer, do 1 + 1 for me. Okay, so now you as a programmer, you will be the one to write this software, the set of instructions, okay? So the computer does not know how to work with these electrons. They know how to make the electrons move and all those things, but they don't know how to use it. So it is you now, it is you that will tell this. All right, sorry guys. At the time, my recording cut. Okay, so let's continue from where we started. Okay, so now the computer does not know how to make use of these electrons to perform anything. So it is your job as a computer programmer to now write set of instructions. All right, in a way that tells the hardware what to do. It is your job as a software developer to write this set of instructions. So this is the role of a software. So the software, when you write software in high-level code, Python or JavaScript, they are compiled into assembly language or machine code, all right? And then turned into binary ones and zeros. Don't worry, we are going to see all these things, okay? Then they are loaded in memory and executed by the CPU. Now, when you write this, when you write a program, when you write a software, this set of instructions, they are stored, all right, in memory. So when you click on, maybe, let's say you click on a calculator app on your mobile phone, this calculator app, all right, will be moved from your hard drive to the RAM. It is from the RAM that the CPU, the control unit, will now be fetching the data from. Don't worry, I don't want to go too deep in that. You'll get to understand better later on. So now, each instruction corresponds to specific transistor switching on and off, zeros and ones, directing electrons to flow in exactly the right way to carry out that instruction. You might not understand what I just said now, but it is fine. Just understand this. The instruction, the set of instructions you write in a software, or we write in a software, all right, they are stored in zeros and ones. All right. And then these zeros and ones, the computer has a way of understanding these zeros and ones. Computer has a way of data representation. They have any zeros or patterns of zeros and ones they see, they know what it is. Okay. So now let's have a reverse order. Okay. We have just talked from electrons to problem. Now let's talk from problem down to electrons. Okay. Now, basically, your computer is to solve a problem. You want your computer to do 1 + 1 for you. That's a problem you want it to solve. So let's go from problem down to electron doing the job. So let's see how it works. So these things are called levels of transformations. All right. Now the thing is, there is a process we must go through to get electrons to actually to do this job for us. Okay. Now you want your computer to do a job for you, but you speak English language, or you speak German, or you speak any language at all. That is not what the computer understands. Okay, so there should be a process from that natural language down to electrons. So let's see how it works. So we call these steps of this process the levels of transformation. All right, and as we will see, at each level we have choices. You have choice not to follow that. At each level you have choice to ignore it, or you don't ignore it. So if you ignore any of the levels, our ability to make the best use of our computing system can be very adversely affected. So you have to follow these levels of transformation. If you choose to ignore anyone, it means that somehow you might not get it correctly. Okay, so the first level is statement of the problem. You have a problem, you want the computer to solve for you. You want the computer to do addition for you. 1 + 1, that's a problem. So you have to state it. So this statement of problem is usually stated in natural language. And natural languages are fraught with a lot of things unacceptable for providing instructions to a computer. All right. Number one thing is that natural languages are ambiguous. You cannot give computer an ambiguous instruction. The computer does not understand ambiguous instructions. But our natural languages are very ambiguous. All right. Sometimes, even if you go to the dictionary, a particular word or a particular phrase can have so many meanings. The computer wouldn't accept that. Natural languages are filled with ambiguity. All right. The way you say something, the tone in which you used to say something can even make the whole somebody to misunderstand it. So natural languages are ambiguous, and to infer the meaning of a sentence, a listener is often helped by the tone of voice of the speaker. So the tone of a speaker can actually change the whole meaning of a natural language. So this is the reason why. First of all, we'll state this problem in a natural language, but that is not what the computer would understand. So from the statement of the problem in a natural language, we will now have to create algorithm. From natural language to algorithm, okay? Then the first step in the sequence of transformation is to transform the natural language description of the problem to algorithm. So first of all, when you want to develop a software, you need to get the problem statement. All right, you need to get the statement of the problem. All right, from the statement of the problem, you can now transform it to an algorithm. And in doing so, you're getting rid of some ambiguity of natural language. Okay, so an algorithm is a step-by-step procedure that is guaranteed to do, number one, to terminate. All right, an algorithm is a procedure, step-by-step procedure that must terminate. At a point, it has to terminate. All right, and such step is precisely stated, and again, it can be carried out by the computer. An algorithm must meet these three criteria. Don't worry, we are going to talk more about algorithm in the later chapter. Okay, so, but algorithm is a step-by-step procedure that you have to follow, and this step-by-step procedure must terminate at a point. All right, and this step-by-step procedure must be stated, each step must be precisely stated, and it can be carried out Every step you state must be it must be something that the computer can actually do. Computers cannot do everything. All right, every computer has set of things that they can do. Do you understand? Every computer has set of operations they can perform, set of computations that they can perform. So you're not going to give a computer what they cannot, what they are not designed to perform. So there are terms to describe each of these properties. Okay, don't worry, we're going to discuss all these things in length when we talk about algorithm in its own chapter. Okay, so from problem statement, which is written in natural language, to algorithm. Then from algorithm, that is where the programmer will now have to write the program using what was written using the algorithm. So all those step-by-step procedures in an algorithm, the programmer will now have to convert them to computer program using a computer language, a programming language. So the next step is to transform the algorithm to a computer program in one of the programming languages that are available, and there are a lot. So in this course, we'll be teaching you C programming language. We'll also teach you C++ and we'll teach you Python, okay? So programming languages are mechanical languages. They are not like natural languages, okay? So they are not ambiguous like natural languages, okay? So rather, they are invented for use in specifying a sequence of instructions to a computer. So now programming languages were invented to use, that is what we use to give computers instructions. Okay, now, therefore, mechanical languages do not suffer from ambiguities that would make them unacceptable for specifying a computer program. Programming languages are mechanical languages and they are accepted to specify a computer program. Okay, from problem statement to algorithm, from algorithm to program, then from program, now we now go to the ISA, the instruction set architecture. All right, now, instruction set architecture. So the next step is to translate your program into the instruction set of a particular computer that will be used to carry out the work of the program. Now, instruction set architecture is just a set of instructions that the computer can actually execute. Now, it is like an interface. It shows you what the computer can do and also tells you how you can actually get the computer to do that. Okay, so the instruction set architecture, don't worry, we'll still talk about it in length, but it is the complete specification of the interface between the programs that have been written and the underlying computer hardware that must carry out the work of this program. Let me break it down a little bit, okay? Every computer have set of operations, set of things they do, all right? So the computer will tell you, with the instruction set architecture, that is where the computer will tell you, these are the things I can perform, these are the operations I can perform. And it will also tell you, this is how you can actually give me instructions to perform these operations. So it is like an interface between the computer programmer and the hardware. Okay, so instruction set architecture of a computer specifies the interface between the computer program, which is the one that you as a computer programmer wrote, that directs the computer hardware and also the hardware that is carrying out these instructions. Remember, you as the programmer you will write these instructions, computer program that will direct the computer on what to do. Now, the computer, the hardware is the one that will carry out these instructions and perform these operations. So the instruction set architecture is like an interface between you, the program that you have written, and the hardware that will carry out those instructions. Okay, so for example, consider the set of instructions that a computer can carry out. Okay, that is what operations can a computer perform and where to get the data that are needed to perform these operations. Okay, so now every computer has set of operations that they can perform. All right, and they also have places where they can get this data and how they can get it. So the operations that computers perform, we call them opcodes. All right, now the data that the computer will be operating on, we call them operands. All right, then how does this computer get the data, all right, that they would use to perform the operation? We call them addressing modes. So addressing modes are actually mechanisms by which computers actually get the data they need to perform a particular operation. So the particular operation is called opcode. the data itself, the data values, we call them operands, and how the computers actually get this data, we call it addressing modes. So if the instruction set architecture of a particular computer comprises of the opcodes, which are the operations that they can perform, the operands, the data they use to work, they can use to perform these operations, and addressing mode, how they can actually access it. But let me not confuse you more. We'll have a chapter dedicated to the ISA of a computer system. Okay. So a data type is a representation of an operand such that the computer can perform operations on that representation. Computers have a particular way of representing the data that they perform operations on. So if you want a particular computer to perform operation on any data, you have to represent it in the way that the computer would understand it. Okay, so the ISA specifies the mechanism that a computer can use to figure out where the operands are located. So this is called the addressing mode. All right, this is the mechanism I call the addressing mode. So don't worry, we'll talk about this. But first of all, we started from problem statement down to creating algorithm for the problem statement. Then from the algorithm, we now create programs like write some code. All right, the program. All right, then this program the next transformation will now be the ISA. Okay, and from the ISA, now every computer, all right, the ISA, let me give you an instance of this ISA. Just like every automobile, automobiles have a particular ISA. Every car has 3 pedals. All right, the first one, we have 3 pedals. Okay, the one in the middle is the brake, the one in the left is like the clutch, and the other one is like the accelerator. So every car has a steering. Every car has 4 tires or something like that. So this is the ISA of a car. Do you understand it? Okay, this is the ISA of a car. So you that is the driver, all right, you will read the manual of that car and you will now know how to drive that car. So you as a driver is like you're the software, the program, all right? Why the automobile itself is actually the ISA. So every car has a particular ISA. Okay, then this ISA can now be implemented in different ways. I know this might somehow be maybe somehow advanced, but try to grab what I'm trying to explain to you. If you understand what an ISA of a computer is, ISA of a computer has to do with the operations that they can perform, the kind of data they can perform on, and the ways they can actually access that data using addressing mode. And then they also provide you with how you can interact with this ISA. So now, this ISA can be implemented in different ways. Every company, now let me give an example of an ISA. The x86 of Intel is an ISA. All right, the microprocessor Intel, the x86. If you check your computer, check the microprocessor, you see it is probably going to be x86. So that is the ISA, that is the architecture, the instruction set architecture of that computer. Now, different companies can implement it in any way they want. And this is the reason why we now have some will be implemented using different technologies, and then they can be faster or they can be more expensive. So the microarchitecture is implementation of a particular ISA. Okay? The microarchitecture is the implementation of a particular ISA, and different people can implement the ISA any way they want. Okay, so each microarchitecture is an opportunity for a computer designer to make different trade-offs between the cost of the microprocessor, the performance of that microprocessor, and then the energy that's required to power the microprocessor. So this in the implementation of this ISA, the computer designer will check, okay, am I creating this microprocessor to be cheap so that people can afford it? In that way, I'm going to use cheap components, use cheap technology. Or do I want it to be fast? That means I will have to use expensive technology, and that will make the computer expensive. So now these are the trade-offs. So cheap computers have cheap implementations of the ISA, while fast and expensive computers have expensive implementation. Let me just put it that way for you. So computer design is always an exercise in trade-off. All right. The designer will opt for higher performance or lower performance, more energy required or less energy required at a greater cost or at a lesser cost. So these are the things that will determine the cost of your computer. Some computers are costlier than others, all right, while others are more expensive. Some computers are faster. So it is in this microarchitecture, it is in this implementation of the ISA that all these trade-offs now come in. So now, when you are now implementing the ISA, which is now the microarchitecture, all right, these microarchitectures are implemented out of simple logic circuits. So the implementation of this ISA are done using logic circuits. So here also there are choices. Okay, so as the logic designer decides how to best make the trade-off between cost and performance. So the logic circuits are the main components of the computer. So these are the hardware that actually perform those operations. So now the logic circuit would the designer can choose to do some trade-off, whether it's going to be expensive or not expensive, faster or not faster, or consume more energy. Okay, so for example, even for an operation as simple as addition, there are several choices of logic circuits to perform the operation at different speeds and corresponding cost. So I believe you understand what we are doing here. So we go from problem statement to writing algorithm for the problem statement, then writing program for that algorithm. Then we now got from program, we now got to the ISA, which is the architecture of the computer. And then we got to implementation of the ISA. Then the logic circuits are what we now use to implement this ISA and create this physical component that perform the operations of this computer. And then the devices. So finally, each logic circuit is implemented in accordance with a particular technology. Okay, so the CMOS circuits are different from the NMOS circuits. CMOS, so the CMOS circuits are different from the NMOS. Now, these are different technologies. Don't worry, you're going to understand them later on as we go on. So basically, this is how electrons actually perform the job. So when you say computer to do 1 + 1 for you or to stream data for you, this is how it is being done from creating the problem statement, creating algorithm, creating programs like writing the code into the architecture of the computer, into the implementation, which is the microarchitecture, and down to the logic circuits, all right, which gives us the device. But remember, before we get to the logic circuits, we started from electrons need to move, all right? Movement of electrons have to be controlled by transistors, and these transistors put together will give us logic gates, and logic gates put together will give us logic circuits, and this is how we build the system. Okay, so in summary, from natural language description of a problem to the electrons that actually solve the problem by moving from one voltage potential to another, zeros and ones, remember, on and off, many transformations need to be performed. If we could speak electron, or if the electrons could understand English, perhaps we could just walk up to the computer and get the electrons do our bidding. But because that is not the case, we will have to do these transformations. All right, we have to follow this systematic sequence of transformations. And in this course, we'll describe each of these transformations. Basically, this is what you're going to be learning. So right here, we are actually teaching you how the computer performs all the things we ask them to do. So as a software developer or as somebody going into tech, you need to understand these things, okay? So we show you how transistors combine to form logic circuits. We show you how logic circuits combine to form microarchitecture and how this microarchitecture implements a particular ISA, okay? So thank you very much. Make sure you do your test. And if there's any assignment, make sure you do your assignment. I will see you in the next class.